Now we're going to look at a special type of Bernoulli equation, something that occurs in nature at some point or other. You may have seen what's called the logistics curve for population growth.
That's the loveliest thing I've ever heard.
Well, great. I'm glad you're really feeling good about that. So anyway, the equation is the change in the population at time t is proportional to the population. That much you would have gotten. This is like a k, but I'll just call it a because I got to use a couple of parameters. But also proportional to the square of the population. Sometimes when the population goes up too much, see, then the population's growth is curtailed, possibly by some limiting factor, like there's only so much food. So A or B are constants related to the particular population growth rate and limiting factor. Rewritten as a Bernoulli, it's also separable, by the way, we have dp dt minus ap equals negative b times p squared. See it? Just take this and subtract it from this part and subtract it from both sides. So it's a Bernoulli, and u equals p to the 1 minus 2, or u equals 1 over p, and p equals 1 over u. dp dt is negative 1 over u squared du dt, and I think we saw one just like that earlier. So making the substitutions for dp dt goes negative 1 over u squared du dt. For p, 1 over u. And for p squared, 1 over u squared. So here is our transformed equation. If we multiply both sides by negative u squared, we get this linear first order du dt plus au equals b, with integrating factor e to the integral a dt, which is e to the at. We multiply both sides by the integrating factor e to the at. The left side would look like the derivative of e to the at times u. The right side is b times e to the at. Somehow it looks like beat, but it's not. B to the a times t. That should be. So now we want to integrate both sides. Well, integrating a derivative, we just drop the integral. Or, sorry, drop the derivative. We got e to the at equals integrating b e to the at. Be careful. When you integrate e to the at, you multiply by 1 over a. So b over a times e to the at plus our arbitrary constant. Now we would divide both sides by e to the at, multiply by e to the negative at, any way you want to say it. So we would get u equal b over a plus c times e to the negative at. But remember, our u is 1 over p. So we got 1 over p times b over a plus c times e to the negative at, or p equals 1 divided by b over a plus c times e to the negative at. Wow. With just a little bit of further algebra. Yeah, okay, just a little bit. We could say multiply by a, numerator and denominator, a over a, so that's 1. And we get rid of this a here, that way we don't have a complex fraction anymore. And this c times a, well, c is arbitrary, so it's just going to be c. So now we have it a little bit nicer. And tell you the truth, in most of the correct forms you see in textbooks, this number right here is a 1. So now we could divide numerator and denominator by b. We'd have a over b up here, 1 here. This is really c over b, but it's an arbitrary constant, so I'll just put c in there. So p is a over b times 1 plus c times e to the negative at. Often in your algebra texts where this would occur, or maybe a pre-calculus text, it will actually look like this. P equals some number a times 1 plus b times e to the negative kt, and that will show up maybe in your bioscience class. And the graph looks like a big stretched out integral sign, and I have a couple of them here drawn, and we'll draw a couple more. Here's if a is 100, and by the way, that sometimes, well, it is a horizontal asymptote, and it's sometimes called the limiting factor of the population. In other words, for what this population is, there's never going to be more than 100 of them. B is just a number where things work out. If you actually know the population when t equals 0, you can solve, putting in that population And if you know A, you can solve that for B without too much of a hassle. And K is just some number here. I could show you what happens if we alter the B, probably not too much. If I make it B equals, like say, 8 instead. Oh, well, sorry, it's supposed to be B equals 8. There, as you can see, that didn't really change things a lot. It still has that stretched out S shape. There it is with 4. I could make A bigger or smaller. Let me make A 200 just to show you what happens then. You don't see where the stretched out part is, but if I put in 200 here, you would see it. So the stretched out S. I could change my K. If I made it 0.05, it would take it longer. I would just have to go out bigger than 50 here. I'd maybe have to go out to, let's say, oh, I don't know, maybe 150. Let's see if that, oh, not 1500. But there, you can see the stretched out S shape. But that's the typical shape of a, maybe put a 0.25 to show you a different one there, see? Still, the stretched out S shape, looking very much like an integral sign, has a horizontal asymptote at the maximum population value. Watch me change it to 50 and it'll drop down substantially. See, and I like the kind of best there. It sort of look better to me than any of the other ones. That one is kind of sharp because my K is kind of big. I'll go back to 0.15. And I don't need to go clear to 150 there. I'll just go to 50. And now it's a real pretty looking stretched out S. But you see I can just change the parameters, but the graph is the same. And that graph is called the logistics curve, and population growth is like that, when the population growth is limited, as is the population of Earth. So,
what do you think?
Well, I hope it was pretty cool.
Well,
Well, was it good?
yes, indeed.
Okay, great.